In this segment, we'll continue our discussion of dynamic programming. We'll start by looking at conditions for the existence and uniqueness of a value function. Then we'll discuss the single valuedness of the optimal policy correspondence. And finally, return to our example of optimal growth. So let's quickly review the basic problem. We have a metric space X, an initial state x0 in X, and the problem is to find a sequence xt that maximizes the sum of discounted one-period returns subject to the transition correspondence gamma. And we're assuming that for any feasible plan, the limit as t goes to infinity of the sum of discounted one-period returns up to t exists, although we allow for the possibility that it's infinite. Then the 5-tuple, the metric space, the initial state, the transition correspondence, one-period return, and discount factor is referred to as a standard dynamic programming problem. And the approach we're taking is to simultaneously solve an entire class of problems that differ only with respect to the initial state. So let's consider conditions for the existence of a solution. We'll assume that the one-period return is continuous and bounded, and the transition correspondence is compact valued and continuous. And let CB of X denote the set of continuous bounded real-valued functions on X. Now this is a complete metric space, and we're going to need this fact to apply the Banach fixed-point theorem in a moment. Next, we define a function t, which is a self-map on the set of continuous bounded real-valued functions on X, based on the definition on the slide. Now let's unpack this definition a bit. Suppose that you've got some point x in the metric space. Then the right-hand side of this expression is a maximization problem that has a solution. It has a solution because u and w are continuous, bounded, and real-valued, and gamma is compact. So there exists some y, not necessarily unique, that maximizes this expression, and the maximized value is going to be the image under t of w of the point x. And that's how t of w is defined. So for any given function w, its image under t of w, is well defined. Now how do we know that t of w is in fact continuous? This follows from the theorem of the maximum. So if you treat x as a parameter and the right-hand side of this expression as a class of optimization problems, then as you vary x, the maximized value of your objective function will vary in a continuous manner. This is what the theorem of the maximum tells us, and you should check that the conditions for the theorem are in fact satisfied in this case. Now the theorem of the maximum also tells us that the solution correspondence, which is the set of values of y corresponding to any given x, is upper hemicontinuous. But it doesn't tell us that it's single-valued or lower hemicontinuous, and we'll come back to this point in a moment. Now based on the last segment where we stated and proved the principle of optimality, you can verify that a fixed point of t is in fact a value function for our dynamic programming problem. Now let's prove the existence of a value function. We want to show that there exists a unique and globally stable fixed point of t, so this is our value function. And furthermore, if you start off with some initial guess w, and you iterate the mapping t, so you compute t of w and t squared of w and so on, this sequence will converge to the same value function regardless of the initial guess. And this in fact is the basis for the method of successive approximations that we used in the last segment. So the global stability of the fixed point tells us that we'll converge to the same value function no matter what our initial guess happens to be. So let's prove this. The first step is to verify that the function t satisfies the two conditions, monotonicity and discounting, that Blackwell identified as sufficient for a contraction. The first condition states that if w is greater than or equal to w prime, then the image t of w must be greater than or equal to the image t of w prime. And this is very easy to verify. The second condition states that there exists some number delta prime in 0, 1, such that t of w plus alpha is less than or equal to t of w plus delta prime alpha for all non-negative real numbers alpha. And this also can be easily verified. If you set delta prime to be any number larger than or equal to the discount factor delta of our problem, you should be able to see that the discounting condition holds. So t satisfies Blackwell's sufficient conditions for a contraction. And since the set of continuous, bounded, real-valued functions on X is a complete metric space, we can deduce from the Banach fixed-point theorem that t has a unique globally stable fixed point. Now, as we observed a moment ago, the optimal policy correspondence need not be single-valued, although we know from the theorem of the maximum that it must be compact-valued and upper hemicontinuous. So let's think about the conditions under which it is in fact single-valued. And I'll state 3 conditions for this, which in addition to the assumptions we've already made, will guarantee single-valuedness of the optimal policy correspondence. First, suppose that X is a non-empty convex subset of some Euclidean space Rn. Second, that the graph of the transition correspondence gamma is convex. So this states simply that if you take 2 points x and x prime in the metric space, and 2 points y and y prime that are respectively in the images of x and x prime under gamma, then the convex combination of y and y prime must be feasible if you start at the convex combination of x and x prime under the transition correspondence gamma. And the last condition states that u, the one-period return function, is strictly concave on the graph of gamma. And this states that if you have two distinct points, xy and x prime, y prime, both of which are elements of the graph of gamma, then the one-period return you obtain at the convex combination of these points should be greater than the convex combination of the respective one-period returns. And if these three conditions are satisfied, in addition to the two we assumed already, which is that u is continuous and bounded, and gamma is compact valued and continuous, then the optimal policy correspondence is single valued. Now the proof of this is not trivial by any means. You can look it up in F.A.'s book, where he uses a slightly weaker condition than the third one on this slide. Now let's finish up by looking at the optimal growth model one last time. So suppose you have some initial level of capital, x0, and your goal is to choose a path of capital levels that maximizes the sum of discounted one-period returns, and these one-period returns are utilities from consumption, subject to the transition correspondence, gamma, and in this case, gamma just requires that the capital you leave for the next period must be somewhere between 0 and your output in the current period. We'll assume that both u and f are bounded and twice differentiable. We'll assume that they're both increasing and concave and satisfy an inada condition at the origin. So u prime of 0 and f prime of 0 are both infinite. And furthermore, f of 0 is 0, so you can't produce without capital. Now you should verify that gamma is in fact compact valued and continuous. You'll see this right away if you just sketch the production function. The one-period return function is continuous by assumption, so our conditions for the existence of a unique globally stable value function are satisfied. And you can check that the value function is strictly increasing. And this is really quite obvious. If you have more capital today, you could increase today's consumption without reducing consumption in any future period. So the set of attainable payoffs expands, and the supremum of this set is clearly higher. You should also verify that the graph of gamma is convex, and again, if you sketch the production function, you'll see this right away. And you should check that the one-period return is strictly concave on the graph of gamma. So the optimal policy correspondence is in fact single valued. Now we know from the theorem of the maximum that it's upper hemi-continuous, and since it's single valued, it must therefore be a continuous function. Let's use p of x to denote the optimal policy function. You should check that the optimal policy function is increasing. In other words, if you have more capital today, you're going to leave behind more tomorrow. This is quite intuitive, but it takes a little bit of work to show it, and it's worth doing. And the implication of this is that optimal plans must be monotonic. If tomorrow's capital is more than today's capital, then the capital the day after tomorrow must be even greater than tomorrow's capital. And since the production function f is bounded, we have a monotonic and bounded real sequence, which of course is convergent. So starting from your initial level of capital, you're either going to have an increasing and convergent sequence of capital levels, or a decreasing and convergent sequence. And let's think about the properties of the limit of this sequence. Now the optimal policy function must satisfy something called a one deviation property. Now what does this state? Suppose you have some optimal policy function p, and you're thinking about deviating from an optimal plan for 2 successive periods and then returning to the original optimal plan. Your initial level of capital today is x, so you can produce f of x, and you consider the set of capital levels y that you could leave for the next period, which are feasible given today's capital and which will allow you to get back onto the optimal plan in the period after next. Now consider the set of values of y that maximize your one-period return from today's consumption, plus the discounted value of the utility from tomorrow's consumption, subject to the constraints that today's consumption must be feasible and you must be able to get back onto the optimal plan after tomorrow. Now the one deviation property says that the optimal choice today must be among the maximizers of this expression. And this is very intuitive, because if this did not hold, then there would be some value of y that differs from the optimal plan, which would increase the sum total of today's utility and the discounted value of tomorrow's utility, while leaving all other utility levels unchanged, in which case your plan could not have been optimal in the first place. Now the one deviation property immediately yields what's called the Ramsey-Euler Equation, or the Euler Equation, which states that optimal plans must satisfy the condition shown on the slide. It's easier to interpret this condition when it's expressed in terms of consumption levels, which you see at the bottom of the slide. Now we saw that this condition held for the special case of a numerical example in the last segment, but now we see that it holds more generally. It says that you can't increase your payoff by cutting your consumption today by a small amount, raising it tomorrow, and then going back to the original plan. So if you're following an optimal plan, it shouldn't be possible for you to increase utility by making small transfers of consumption across successive periods. Now let's think about the steady state. Since the optimal consumption path is monotonic and bounded, it's convergent. And if we let x bar denote the steady state level of capital, then you see immediately from the Ramsey-Euler equation that the slope of the production function at x bar must be the reciprocal of the discount factor. Now this is referred to as the golden rule investment level, and it's independent of the one-period return function. And furthermore, the steady state consumption level, which is f of x bar minus x bar, is increasing in delta. In fact, if delta approaches 0, so you're extremely impatient, then the slope of the production function approaches infinity, and so the steady state level of capital is close to 0. You see that from the Inada condition. So if you're extremely impatient, no matter how large a level of capital you start off with, you're going to consume most of it and end up converging to a very low level of capital. On the other hand, if delta is close to 1, so you're extremely patient, then the slope of the production function at the steady state is approximately equal to 1, and that's the point at which the consumption stream is in fact maximized. So no matter how small the level of capital you start off with, you'll build up your levels of capital until you reach a point at which you're approximately maximizing the long-run consumption stream. Now notice that even though it's called the optimal growth model, there's no growth in the steady state. You get monotonic increases or decreases in the level of capital, followed by a steady stream of consumption. And the greater the level of patience, as captured by the discount factor delta, the greater the steady state consumption level. And that's it for this segment.